Today, let's look at loops in my research spreadsheet environment, Planarly. Say we wish to add I to the ith element in a list of numbers in a conventional spreadsheet. The initial list is 9, 3, 4, and 7. We first drag to generate the list of numbers to add. Then, we drag to apply the addition operation to all the rows. Spreadsheet users habitually rely heavily on copying and pasting cell formulas. It's convenient, visual, but very fragile when subsequently edited. We don't discuss this approach further, as code duplication is the cardinal sin in programming. Instead, in Planarly, we try to use vector operations. For problems where vectorization is possible, this is the preferred approach in Planarly. Conceptually, it is identical to NumPy in Python. No explicit loop required. Unfortunately, not every loop can be expressed this way. For general-purpose loops, several approaches are common in existing languages. Most mainstream languages have an imperative control structure, usually some variation of the C loop. But I don't want this in a cell formula. It's too flexible and undisciplined, and more importantly, it relies on mutable loop counters. Mutability is an alien concept to spreadsheet users, and I wish to keep it that way. Functional languages don't use mutable loop counters. They typically have recursion in place of loops. Unfortunately, recursion is something that I hate having to explain to the average spreadsheet user. If we wish to empower experienced spreadsheet users to program properly, my favorite approach to loops is Python's list comprehension. This expression is still functional, but having a dedicated syntax allows for very user-friendly code. In fact, the inventor of Python, Guido himself, famously wanted to remove the map, filter, and reduce functions and use list comprehension exclusively. Of course, spreadsheets being two-dimensional beasts need to adapt the definition to work on tables. Let's see how table comprehension works in Planarly. Let's digest the syntax slowly. In a Planarly table comprehension, R and C are the built-in loop variables, the row number and the column number respectively, both starting from 0. The expression evaluates the R equals 0 row until the whole clause is no longer satisfied at C equals 5. Then it moves on to the R equals 1 row, sweeping cell by cell till the whole clause fails at C equals 4, and so on. When row R equals 5 fails to generate any cells, the whole expression terminates. Cells can be skipped with the optional if clause. Here, only the even rows are kept due to the divisible by 2 if clause. If an R is missing, then we only loop through the C's, so we can also generate a triangle column by column. Likewise, if C is missing, then we only loop through the R's. So back to the problem of adding I to the ith element in a list, we can write this expression to loop through the height of the input. But the while clause is cumbersome. When R and C are used as table indices, Planarly allows the while clause to be omitted. The boundaries of R and C are then what's allowed by the index range. So we can write this simple formula to express our array addition. Let's now try the FizzBuzz problem. It's often used as an easy first question in programming interviews to filter out candidates who cannot program at all. And legend says that a surprising number of interviewees fail anyway. Let's see the question on LeetCode. Given an integer n, return a string array starting from index 1 depending on what I is. We can translate this requirement literally to a Planarly table comprehension. Since our R starts from 0, the I in the question is in fact R plus 1, which starts from 1. If I or r plus 1 is divisible by 15, we show FizzBuzz. Otherwise, if I is divisible by 3, we show Fizz. Otherwise, if I is divisible by 5, we show Buzz. Otherwise, we show I, while r is less than n. One, 2, Fizz is correct. So is when n equals 5. Or, when n is 10. Congratulations, you just passed the first interview question. Let's see a final example today, where at each R and C we generate not a single cell, but a proper table, introducing the z-order curve. The z-order curve visits all cells in a square in a particular order. The smallest squares, of the 2 by 2 cells, are visited in the shape of the letter z. A bigger square, of the 4 by 4 cells, is visited quadrant by quadrant, also in the shape of the letter z. Same for the even bigger 8 by 8 square. Let's write the code to generate this z-order curve table in Planarly. We make a sheet as function, z, to take one z-order curve and make a bigger one. We use a simple input 1 and 2 above 3 and 4, and the 2 by 2 z-order curve table that's the basis of all bigger tables. And the desired output, which is the bigger z-order curve, looks like this. We wish to expand the cell 1 to a square 1, 2, 3, 4, and the cell 2 to a square 5, 6, 7, and 8. So the general formula is the input cell times 4 minus 3, minus 2, minus 1, and minus 0. Now, we can write out the table comprehension. The expression generates a 2 by 2 table for every R and C, which are put together to form the return value. If we add a barrier here to avoid any possible spill conflict, then we can test this sheet as function in our main sheet. The simplest z-order curve is just 1, and p.z hash input expands it into a 2 by 2 square. If you are unfamiliar with sheet as functions, then you can watch my previous episodes 3 and 4. The links are in the comments section. If we wrap the formula in one or more calls of p.z, we can get the bigger squares 4 by 4, 8 by 8, and so on. This concludes today's video. Next week, we'll see more advanced table comprehension, where we need to reference the values just evaluated for previous R's and C's. I hope you liked the ideas in this video. Planarly is my Affero GPL licensed open source research project. You can try it live at planarly.com in Chrome. The application runs entirely in your browser. Your data never leaves your computer. Follow me on Twitter, Dr. Planar, and see you next time.